Do you understand how the Bitcoin system actually works? I didn't, and decided I wanted to change that. There are certainly plenty of materials describing the system, but when I started reviewing publications and videos, I found many described the system at quite a high level, which didn't really leave me with a very strong understanding. Other materials were very detailed, but more directed to a computer programmer rather than to the average person, and somewhat hard to understand. But with my background in electrical engineering and patent law, and with some persistence, I eventually ended up with a decent understanding of how the system actually works. And then I thought, maybe there are others who would like to have a stronger understanding of the Bitcoin system, even if they don't have a technical background and don't have months to try to figure it out. In my career, I spent decades learning new inventions and writing patent specifications describing these inventions in an understandable way. So I hope I have the skills to prepare some videos that will give you a strong understanding of the Bitcoin system, even if you have no background in technology. Well, that's what I'm going to try to do, so let's get started. The Bitcoin system was created in 2009 as a digital currency. In other words, a currency that exists only inside computers. A major feature of the Bitcoin network is that it is decentralized. Because of this, the Bitcoin network is not controlled by any single entity nor by any government. To understand the Bitcoin system, let's start by looking at two concepts that Bitcoin and other cryptocurrencies took from the field of cryptography, which are crucial to making the Bitcoin system work. The first of these concepts is cryptographic hash functions, and the second is digital signatures. So, what is a hash function? The most simplified explanation is that it's a function that scrambles a message. For example, here's a simple message, written as ones and zeros, since this is what any message is converted to inside a computer. In computer lingo, each one and each zero is called a bit. The message is shown as being run through a hash function, which is illustrated as a box, and the output of that function is a hash, which I think you will agree does not look anything like the original message. So, what's going on inside the box? The hash function that changed our message to the illustrated hash could be the following: a rule that divides the message in half and then combines the two halves in an exclusive OR operation, often written as XOR and pronounced XOR. With an XOR operation, at each bit position, 2 zeros or 2 ones results in a 0, whereas 1 1 and 1 0 results in a 1. Applying these rules to the message 11010011, the message is broken in half to obtain an A part 1101 and a B part 0011. These A and B parts are then stacked so that an XOR operation can be taken on each pair of stacked bits in order to obtain the hash H. In the leftmost bit position, A is 1 and B is 0, so the XOR operation on these two bits is 1. On the next bit position, A is also 1 and B is 0, so again, the XOR of these two bits is 1. In the third bit position, A is 0, B is 1, so the XOR of those two bits is again 1. And in the last bit position, the A is 1 and the B is 1, so the XOR of those two bits is 0. Well, the example hash function was very simple. A cryptographic hash function is more complex and has the following characteristics. It's a one-way function. With a message in the hash function, you can determine the hash value, but with the hash and the hash function, you cannot determine the message. It's almost impossible to find two different messages that produce the same hash. And lastly, you cannot figure out what message you would need in order to obtain a specific hash. Indeed, if you change just one character of a message, this typically results in a very different hash. Okay, what about our simple hash function? It took the message 11010011, broke it into two pieces, an A part 1101 and a B part 0011, and generated the hash 1110. So if we know the hash function and the hash, can we recreate the original message? Well, if we pick A as 0101 and B as 1011, we get the hash value we want, 1110. But wait, these are not the A and B values of our message. Also, if A is 0000 and B is 1110, we also get the same hash value. And we get the same hash if A is 1100 and B is 0010, or if A is 1001 and B is 0111. Yikes! So there are a number of choices for A and B that will result in the same hash value. Consequently, you can see that even though we know the hash value and the hash function, we're not able to figure out what the message was. Therefore, even our simple hash function has the property of being a one-way function, which is one of the features of a cryptographic hash function. Also, even though our hash function was simple, the XOR operations it used are one of the one-way operations that can be found in actual cryptographic hash functions. Bitcoin uses a couple of different cryptographic hash functions, but the main one it uses is named SHA-256, pronounced SHA-256, where SHA simply stands for Secure Hash Algorithm. This function converts a message, no matter what its size, to a hash, which is 256 bits long. That is a number that's 256 digits long, with each digit being a 0 or a 1. A 256-bit number is really big, much bigger than the number of grains of sand on the Earth, and in fact almost as big as the number of atoms in the known universe. So it's certainly big enough to avoid collisions, that is, to ensure that no two messages result in the same hash value. To ensure the next point is understandable, note that in computer science, numbers are often written as hexadecimal numbers, which is a way to write a big number with less digits. In a hexadecimal number, the numbers 0 to 9 are the same as in our usual numbering system. However, the numbers 10 to 15 are represented by the letters A through F. So, for example, if you see the letter E in a hexadecimal number, that's the number 14. We can take a SHA-256 hash of our message 11010011 to get a 256-bit hash value. This 256-bit hash value is written as a 64-digit hexadecimal number on the screen. But what if we changed our message to be 11010010, which differs from our original message only in the last bit? As you can see, the resulting SHA-256 hash is a completely different number. It should be clear from this that there's no way to figure out what message you would need in order to obtain a specific hash value, which is the third requirement for a good cryptographic hash function. Bitcoin uses hash functions for a variety of purposes, such as for ensuring the integrity of data and in a process called mining. These uses of hashes in Bitcoin are discussed in later videos. The second concept from the field of cryptography that's used by Bitcoin is that of digital signatures. Digital signatures rely on public-private key pairs. A user, Alice, picks a random private key and then generates a public key from the private key using agreed one-way functions. An example 64-digit hexadecimal private key D is shown, as is a public key Q derived from the private key. So the keys are just numbers. Perhaps when you think about public-private key pairs, you think of spies. If Alice is a spy, she can ask another spy to use her public key to encrypt messages to her, and then Alice can use her private key to decrypt these messages. As suggested by the names, the private key must be kept completely private, but the public key can be shared. But there's another important use for public-private key pairs, and that is in creating digital signatures. A digital signature can be used to prove a message came from the sender. How does that work? After Alice creates her message, she picks a random number and uses a one-way function to determine a second number, R. The number R, the message itself, and Alice's private key are used to populate certain mathematical operations on an elliptic curve in order to determine one more number, S. Alice's digital signature is the number pair RS, which she sends along with her unencrypted message to Bob. Bob gets the message and reads it. But is it really from Alice? Bob undertakes certain agreed mathematical operations on the same elliptic curve using S, the message, and Alice's public key. The operations are chosen so that the number resulting from the operations will be R only if S was created with Alice's private key. But only Alice has her private key. Consequently, if the resulting number is R, Bob knows that the message has to have been from Alice. On the other hand, if someone substituted a different message with Alice's digital signature, Bob would recover a different number, not R, when performing the agreed operations using the received message. This would inform Bob that the message could not be confirmed to be from Alice. In the Bitcoin network, a digital signature is used in proving ownership of Bitcoin. But how does that work? In the Bitcoin network, the messages are records of Bitcoin transactions, and all past transaction records are stored on the network. Each transaction in a transaction record has an address for a recipient of some Bitcoin. Importantly, in every transaction, the address for the recipient of the Bitcoin is derived from a public key of the recipient. If Alice receives some Bitcoin in a prior transaction and now wants to spend it, she must prove she owns it. She does this by creating a new transaction record, which identifies the prior transaction and includes her public key, which was used in deriving the recipient address in the prior transaction. We'll call this public key Z. She then digitally signs a hash of her new transaction record using her private key Z, which is paired with her public key Z. She digitally signs a hash of her record rather than the record itself in order to provide a fixed-sized input for the signature algorithm. Alice then stores her digital signature in the new transaction record. When the new transaction record is sent to the Bitcoin network, the network grabs public key Z from the new transaction record and derives an address from it to check that the address matches the address in the prior transaction record. If there is a match, the network knows that Alice is in possession of the public key from which the address was derived. But is it really Alice's public key? To answer this, the network undertakes the agreed operations using the number S from Alice's digital signature, public key Z, and a hash of the new transaction record to determine if these operations return the number R from Alice's digital signature. These operations will return R only if Alice's digital signature was created with private key Z. So if R is returned, the network knows that Alice has to be in possession of private key Z, and concludes from this that public key Z is indeed Alice's public key. If public key Z is Alice's, the network knows the Bitcoin transferred to an address derived from public key Z is Alice's. So, Alice has proven she owns the Bitcoin from the prior transaction. With that background, we're now ready to delve into the Bitcoin network with a quick overview, and then by first looking at transactions and blocks. You can find the next video by subscribing to this channel or clicking on the above link.